Did we do this in the last class? Or? No, right? Okay. So VThevenin, voltage across A and B terminals. So considering only 12 volt source, I'm using superposition theorem to find it. Superposition, or directly you can use a nodal analysis. Okay, let me have a V here. V minus 12 by 3 minus 1 plus V by 6 is 0. V by 3 plus V by 6 is equal to 12 by 3 is 4 plus 1 5. So that implies 6 2 2 plus 1 3 V by 6 is 2. V is 10 volts. Right? VThevenin is 10 volts. Okay. And then RThevenin. What is RThevenin? Anyone? RThevenin. Open this, short this. 6 parallel with 3, 2 ohms. Okay. VThevenin and RThevenin. Next, you can find this circuit shown the Norton equivalent resistance across terminals A and B. Norton equivalent resistance across terminals A and B. And coming to resistance, it's same as Thevenin's equivalent resistance. So how do you do this? So what kind of source is this? What kind of source are you seeing? This is a dependent source, current dependent voltage source. The value of this voltage source depends upon the current here, right? Yeah. Now, how to do this? This is something called as a dead circuit. What's a dead circuit? If there is no independent source, then it is called a dead circuit. How to solve a dead circuit? Activate the circuit using a independent source, a voltage source or a current source of known value, 1 ampere. Okay, find VAB now. Call this V or VAB. V by 1 will give you resistance, RThevenin. So this will be V minus 4I by 2 plus V by 2 nodal analysis plus V by 4 minus 1 is equal to 0. And what is I? I is equal to, okay, I is equal to V by 4. So V by 2 minus 4 into V by 4 plus V by 2 plus V by 4 is equal to 1. So V by 2 plus V by 2 is V minus V. So V by 4 is equal to 1. V is equal to 4. Right? So R Norton is equal to 4 by 1, 4 ohms. So how much did you get? 1.33. Check it.
Sir, actually in the intermediate step itself, I equal to E by 4 is written. So from there itself, we will get 4 ohms, right, sir? Just cross multiplying.
I is equal to? No, I didn't understand.
Uh,
In second line, it will be 2i, na, sir? V by 2 minus 2i will be there, no?
Okay. Yes, yes. Right. Okay, V by 2 minus 2 into I is V by 4. Okay, sorry, correct. Plus V by 2 plus V by 4 is equal to 9. Because V by 2 and V by 2 gets cancelled. So this will be 3V by 4 is equal to 1. V is equal to 4 by 3. Okay, so R and R Thevenin is V by I, which is 4 by 3 ohms. Correct. Okay. So find the maximum power that can be delivered to the resistor R. Find the maximum power that can be delivered to the resistor R. Important one. Try to do this. Find the maximum power that can be delivered to resistor R. So again, everyone, what kind of source is this? This is a, what kind of source is this?
Voltage controlled voltage source.
Voltage controlled voltage source. This is a voltage source whose value is controlled by this voltage. Okay, now calculate the maximum power that can be delivered to the resistor R. So for that, what you have to do, find the Thevenin's equivalent across this resistor R. Find the Thevenin's equivalent V Thevenin and R Thevenin across this resistor R. So first thing, what is V Thevenin? To find V Thevenin, 800 watts. Okay, V Thevenin 5 volts, 3K and 2K, V naught. This is 40K and 10K. This is 100 V naught. So what is V naught from this? 5 volts, 3K and 2K. Directly V naught is voltage division rule. These two are in series. 2 volts, right? 5 into 2 by 5, 3 plus 2. This is nothing but 2 volts. V naught is 2 volts. So this will become plus minus 100 into 2 is 200. And you have 10K over here and 40K here. So V Thevenin will be 200 into 40 by 50. Right? So 200 into 40 by 50. So it's 160 volts. Okay. Okay, everyone. 160 volts is V Thevenin. Next, R Thevenin. To find R Thevenin, what should you do? You should short the independent source or turn off the independent source. When you turn off independent source, what is V naught? V naught is 0. Directly V naught is 0. So this value will be 0. Okay. So 0 volts is a short circuit. So this will be the circuit. 40K and 10K parallel. So R Thevenin is 40 parallel to 10. 400 by 50. 8K. Right? So V Thevenin 160 and R Thevenin 8K. So maximum power delivered is V Thevenin square by 4 into R Thevenin. V Thevenin is 160 into 160 divided by 4 into 8. So many milliwatts. $800 milliwatts. P max is 800 milliwatts. Okay.
Yes, sir.
Yeah. Find this. Determine thevenins and nortons equivalent between A and B terminals. Find this. Determine thevenins and nortons equivalent between A and B terminals. What is R thevenin? What is R thevenin?
30 parallel with 40, 90, no, sir?
Yes. Right, R thevenin directly. Open this current source. You'll have something like this. 10, 20, 50 and 40. 10 and 20 are in series, which is parallel with the 40 and 50. So 30 parallel with 90. 22.5 ohms. Okay. Now you can either find VThevenin or RThevenin. So how to find VThevenin or RThevenin here? So how do you want to do this?
So resistance is equal in both the arms, so 8 ampere will be divided into equal. So VTH will be the voltage across 50 ohm minus voltage across 40 ohm.
Yes. So as you can see, these two are in parallel. So 50 and 10, 60, 40 and 20 is 60. So equal resistances divide current equally. This is 8 amps. So 4 here and 4 here. So what is this VA? VA is 4 into 50. VB is 4 into 40. So VA minus VB is nothing but VThevenin, which is equal to 4 into 50 minus 40 volts, right? VThevenin. So what is IN? What is IN? So either you can do what? VThevenin by RThevenin.
Convert. Okay.
Yes. Convert the Thevenin's equivalent into nortons. So 40 by 22.5. Okay. Is this. Okay. Clear so far? Let's go to the next topic. Okay, capacitors and inductors. L and C elements or C and L elements. Capacitors and inductors. Next topic is capacitors and inductors. So we have three passive elements: resistors, inductors, and capacitors. R, L, C are all passive elements. Okay. So a capacitor is an passive element designed to store energy in its electric field. A capacitor consists of two conducting plates separated by an insulator. Two conducting plates separated by an insulator called as dielectric. Okay. So there is positive plate and negative plate. Okay. The amount of charge stored represented by Q and is directly proportional to voltage V. Okay. The amount of charge that is stored between these plates is proportional to V. Q is proportional to V. And what is a proportionality constant called as C. C is capacitance of the capacitor, similar to resistance of a resistor, capacitance of capacitor, and is measured in farads. Okay, capacitance of capacitor, capacitance as similar to that of resistance is a physical quantity. Okay, it depends upon physical property. Capacitance is a physical property. Okay, similar to that of resistance. The amount of charge stored represented by which is represented by Q and is directly proportional to the applied voltage. Okay, this is how you represent a capacitor. Two plates. Okay, current I, C, and this is voltage V, where C is the constant of proportional and is known as capacitance of the capacitor. Unit is farad. As every physical, what you call physical element, as I told, capacitance is a physical property, depends upon the area as well as the diameter. It depends upon the physical properties. Similar to resistance, resistance depends upon area and length. Capacitance also depends upon area and diameter. Distance between the plates. C is epsilon A by D. Epsilon epsilon is equal to epsilon naught epsilon r A by D. What is epsilon? Epsilon is nothing but permittivity. What is this? This is nothing but permittivity. Okay, epsilon naught, absolute permittivity and relative permittivity. What is epsilon naught value? Absolute permittivity value of absolute permittivity. Anyone?
So 8.854 into 10 to the power minus 14 farad per centimeter.
Correct. 8.854 into epsilon naught is equal to 8.854 into 10 power minus 14 farad per centimeter or meter. Okay. And what is epsilon r? Epsilon r is relative permittivity and it depends upon centimeter, and it depends upon the material, dielectric, depends upon the dielectric between the plates. Okay, and A is area, cross sectional area. D is distance between the plates. Okay, voltage and current relationship of a capacitor. See, we have Q is equal to CV. And what is current? Current is nothing but rate of change of charge. We have seen uh, in the first class. I is dq by dt. So what is I? I is nothing but dy dt of CV, which is C dV by dt. So current and voltage equation is I is C dV by dt. Okay. So from this, if you can see, there. So the property of capacitance is something like this. Or I can write C is integral, or C is equal to I dt is equal to C dV. Okay, or C is equal to 1 by V integral I dt. Okay, so from this you can see that whenever there is a change in voltage, okay, whenever there is a change in voltage, there is a current. Okay, or the current flowing through the capacitor opposes any change in voltage. Okay. Next, energy stored in a capacitor. Energy is integral p dt. P is v into I dt. We have just seen integral v into c dv by dt into dt. So this is integral vc dv, or c into integral v dv, or v by 2, v square by 2, sorry. So energy is equal to half cv square. Energy stored in a capacitor is half cv square. Okay. So these are the remarks for a capacitor. If the voltage across the capacitor is constant, then current through the capacitor will be zero. That means the capacitor acts like an open circuit for DC. What we have, I is equal to C dV by dt. That means if there is any change, or like constant, there is no change in voltage, dV by dt is zero. If dV by dt is zero, I is zero. Okay, what does an I0 indicate? It indicates an open circuit. Okay, so for DC voltages, capacitor acts as an open circuit. For DC, capacitor acts as an open circuit. Remember this, for DC, capacitor acts as an open circuit. Okay, the voltage across a capacitor must be continuous. If the voltage across the capacitor is discontinuous, then the current I CV by dt will be infinite, because the derivative will be infinite in that case. Thus, the voltage across the capacitor cannot change instantly. So I is C dV by dt. If voltage, there is a change in voltage instantly at dt is 0, so I becomes infinity. I tends to become infinity. So there will be infinite current, right? Infinite current, so which cannot be possible. So capacitor always opposes any sudden changes in voltages, or any instantaneous changes in voltages. Capacitor will oppose. Okay, capacitor always opposes any instantaneous changes in voltage. That means voltage across the capacitor must be always continuous. Okay, a capacitor never dissipates energy, it only stores energy. So energy stored in a capacitor is half CV square. We just seen it, half CV square. Okay, capacitor never dissipates any energy, it only stores energy, half CV square. It stores energy in the form of electrostatic field. Okay, resistor dissipates energy in the form of heat. Capacitor dissipates stores energy in the form of electrostatic field, and inductor stores energy in the form of electromagnetic field. Okay, so this is about capacitor. Okay, capacitor acts as an open circuit to DC. Okay, next, capacitors in series. Okay, next topic, capacitors in series. Okay, this is V1, V2, C1, C2, C3, and so on. Okay, this is voltage V1, V2, V3, and so on. So V is equal to V1 plus V2 plus V3 plus 1. So this is and remember this, in series capacitors, the charge is same. Okay, charge is same. Similar to that of current, same in case of resistors. In series capacitors, charge is same. So you can say something like this. Or you already have the C is equal, sorry, I is equal to C dV by dt. From this you have V is equal to 1 by C integral I dt, right? So from this, if I write, this is 1 by C1 integral I dt, because series current is also same. So I dt plus 1 by C2 integral I dt plus 1 by C3 integral I dt plus so on. So this can be equivalent to 1 by C equivalent integral I dt. So if I take integral I dt common, this will become 1 by C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C3 and so on. Okay, so C equivalent is something like this for two capacitors. Two capacitors. If there are only two capacitors, C equivalent is C1 C2 by C1 plus C2. Okay, so this is like capacitors in series is like resistors in parallel, right? Equivalent resistance in parallel is 1 by R, equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on. Similarly, for capacitors in series, it's like 1 by C equivalent is 1 by C1 plus 1 by C2 plus 1 by C3 and so on. Okay, and remember current as well as charge are same in case of series capacitors. Okay. Next, capacitors in parallel. Capacitors in parallel. I'll take a voltage source V, C1, C2, C3 and so on. Okay. So you have I is equal to I1 plus I2. So this is I1, I2, I3 and so on. I1 plus I2 plus I3 and so on. I1 is C1 dV by dt. So voltage is same because of parallel circuit. C2 dV by dt plus C3 dV by dt and so on. This is C equivalent dV by dt. So C equivalent is C1 plus C2 plus C3 and so on. Okay, so capacitors in parallel are like resistors in series. Capacitors in parallel are like resistors in series. Okay, clear so far? So
Clear.
capacitors in series are like, what happened?
I was just telling it's clear.
Okay, okay. Okay, that's about capacitors. Next is inductor.
Sir, sir, if two capacitors have their initial charges, in that case, if we connect them in a parallel formation, so can we find the overall capacitance in that formula by using that formula?
So you are definitely talking about transients. I'm not talking about the transient case. Okay, this is a steady state case. Okay, this is a steady state case. We will see it in transients. Transients are like those instantaneous movements, right? So those instantaneous
Yes, sir.
movements, everything changes. It won't be like, capacitors, as I told you, in for DC, it acts as an open circuit and all. Those when I go into the first order and second order circuits or the transients, I'll bring them out. Okay. Okay, this is for
Okay,
general capacitances. Okay, capacitors in series and capacitors in parallel. When we see transients, then we'll see that. Okay, this is for a steady state condition. Okay.
okay. Means all equivalent condition like for series and parallel we have considered only for the steady state condition, no, sir?
Right. See, and again, when you see AC circuits, steady state AC, sinusoidal steady state AC circuits, what happens is again, this, as I told you in series, all the capacitors are like the equivalent capacitance is nothing but 1 by C1 plus 1 by C2, like simply as a resistors in parallel. But when comes
Yes,
there, there is something called as capacitive reactance. And capacitive reactance is again, XC equivalent is XC1 plus XC2, XC3. Okay.
yes, sir.
XC is again, what is XC? 1 by omega C, right? If you remember,
Yes,
or
sir.
1 by 2 pi of C. So again, all those changes when we see AC circuits, we will see all those. Okay, sinusoidal steady state AC circuit. This is for capacitors. Okay, this if you remember, you might have studied in electrostatics, even in your what you call +2.
Yes,
Okay.
sir. Okay, sir.
Yeah. Next, inductor. An inductor is a passive element designed. Saying something. Okay, an inductor is a passive element designed to store energy in its magnetic field. Okay, what does an inductor do? Inductor stores energy in the form of magnetic field. Okay, an inductor consists of a coil of conducting wire, something like this. Okay, inductor is nothing but any coiled coil. Okay, if you take a wire and you spiral it, it becomes an inductor. Okay, if you do it on a what you call magnetic material, its magnetic properties will improve. Otherwise, on air also there will be. Okay, so there will be the current flowing through the inductor will have some magnetic field around it. Okay. Okay, next. So again, psi or magnetic flux linkages is nothing but psi. Psi is nothing but your flux linkages, which is proportional to the current flowing through it. Okay, which is proportional to the current flowing through it. So what happened?